right, hello there. So this is video 3 of section 3.1. Here I'm actually just going to do two examples. I'm going to do the example from the end of the worksheet in corresponding to the first video that I didn't do there. So this will be finding the determinant of this matrix. And then I'm going to do the example at the end of the next video. So basically, if you look at the section 3.1 worksheet, I'm going to do the two examples that I did not cover previously. So we're just going to find a couple determinants, go through the steps again, just to get more practice. And so I highly, highly recommend, if you have not already tried these on your own, to do so. They're very similar to the other two examples I gave, and so working through those same steps, you should be able to find these determinants. And so definitely try those before watching this. So let's get right into it. All right, so there's actually nothing spectacular to this, and at this point you might have watched video 2, but for now I'm actually still going to expand across the first row. So I'll use the original definition of determinant that we gave. What I do want to introduce is a slightly new notation for the determinant of a matrix, which will sometimes save us a little bit of time. If we provide a matrix and draw these straight line brackets, this is meant to indicate determinant. So be very careful with that, because I think often starting out with linear algebra, it's tempted to just write normal matrices like this because it saves a little bit of time and it looks neater. But just be very, very careful, because this absolutely means determinant. And so definitely always write your matrices with brackets or with big parentheses as well. So anyways, so this notation will often be used now for determinant of a matrix. All right, so if we expand across the first row, well, I want to take each entry, so I'll start with 0, and then I want to multiply it by the determinant of the corresponding submatrix, and so I want to delete column 1, row 1. I'm left with those 4 entries. All right, now I subtract 4 times the correct submatrix, 5, 0, 2, 1, where again I've just deleted the column and row that 4 is in. And then I'm going to add 1 times the determinant of 5, 3, 2, 3. All right, so working through this a little more. Well, this 0 just completely, this term cancels out. So we can just start with the negative 4. So that's going to be 5 times 1 minus 2 times 0. Again, once we get to finding determinants of 2 by 2 matrices is where we sort of actually break it down in a sense and start to do some real calculations. And so then we're going to add 1 times 5 times 3 minus 2 times negative 3. All right, and so now it's just a matter of doing some arithmetic, which, like I've said, scares me more than some of the other stuff in many ways. But so this is negative 4 times 5 minus 0 is 5, plus 1 times 15 plus 6 is 21, which is equal to negative 20 plus 21, which is equal to 1. I feel like in math, anytime you work through a problem like this and get 1 as your answer, you can be pretty confident and correct that, if you were going to get some random number out, it's very unlikely you just get 1, and very unlikely that you would get 1 and wind up with the correct answer if 1 wasn't the correct answer, I guess. But it happens, certainly. I do sort of have that bias, though, working through problems that, if I don't wind up with with like a very, very nice number that I always get worried. Like I get convinced that I did something wrong if I don't get a very nice answer because I've been so conditioned to want those very nice answers. So we'll finish up with one more example. So we want to find the determinant of A if A is the following matrix. So here A is going to be a 4 by 4 matrix, and there's actually going to be something here that is going to lead into the start of next section. All right, so remember with this, we have the trick of being able to expand across any row or column. And so with these, we're generally just going to choose the row or column with the most zeros. So I think I'm going to start by expanding across row 4. So this means that the determinant of A, and I'm going to shorten things. Well, we'll do. So this is 0 times the determinant. It's actually minus. No, hold on. We'll write out the full formula. So if we're expanding across this, 0 is in the first row, 4th column. So this would be -1 to the 1 plus 4 times 0 times the determinant of the corresponding submatrix. 5, -6, 4, -2, 3, -3, 0, 1, 5. Or again, I've taken this, deleting this row, this column, and worked everything out. So I'll do it for this term. For the next 2 terms, I'll just write out zeros. So notice, again, this is the full formula. If this term wasn't 0, then we would have a little more work to do. But so notice the next term, again, is just going to get zeroed out. The next term, again, is just going to get zeroed out. And so we actually don't have anything to do until we get to this 3. So now this is going to be plus -1. 3 is in the 4th row, 4th column. So to the 4 plus 4 times 3 times the determinant of, well, I'm going to delete column 4, row 4. And so I want to multiply by the determinant of this matrix here. And so notice the nice thing about choosing row 4 is actually the first 3 terms of this calculation, which would normally be all involved, as involved as this term, just go away. So I only have to worry about working this out. Well, notice that this again might be fairly easy, well, relatively easy, I guess, because I'm just going to now expand across this row. So this is equal to, well, this 1 just, -1 goes away because it's a 4 plus 4, times, so if I expand across this row, I get 0, plus 0, plus 1, times the determinant of 3, 5, 0, -2. And again, because these zeros sort of just zero out these first 2 terms, so I only have to worry about the corresponding term, this term corresponding to this 1. Well, now this is equal to 3 times 1 times 3 times -2 minus 0 times 5, which is actually equal to 3 times 1 times 3 times -2. And so notice for a second that these 4 numbers are the 4 numbers that lie on the diagonal of A. And so the determinant here is equal to -18, and that's our answer. But just observe that we found this by multiplying all of the numbers on the diagonal. And so this is sort of hinting at where we're going to go. A is an upper triangular matrix, right, because it has zeros below the diagonal, and its determinant was equal to the product of the entries on the diagonal. And I will tell you now that is not a coincidence. But we will see more of that in section 3.2.